For this kind invitation to the CIRM, where I'm here for at least 25 years, already as a PhD student when I was giving my first talk on the limit from Schrödinger-Poisson to Vlasov-Poisson. So to present you today the Quantum Vlasov equation and its usefulness for the community, especially in cosmology, is a pleasure. So I will give a blackboard talk to introduce the key ideas. You find many details, it's quite complicated in the papers I refer in my abstract. So before we talk about quantum Vlasov equation, let's briefly write down the key element of the classical Vlasov equation. So we have a phase space distribution, which is non-negative, and our density, the macroscopic object, rho, would be the moment in velocity. And then this is just a brief recall, and then we have the Vlasov equation. Let's write it down in this way for this F. Let's write it down symplectically. The gradient of a potential. Okay, so this would be the equation all of you know. That's what this conference is about. So assuming that this potential is given, it's sometimes called the Liouville equation, but in this community, the consensus, we call it Vlasov equation. So when we calculate the potential, let's take both lines, from this density, we call this the Vlasov-Poisson system. Okay, so that's what all of you know. That's just a warm-up. Now, what would be the quantum situation? Okay, sorry. Okay. So in quantum physics, that's maybe not known to all of you. So the quantum case would be, we do not work with a probability distribution, we work with a wave function. This famous complex valued function in position, space, and time. So we're already in physical space, and then let's say we define our density as the square of the modulus. And that's again a non-negative function. Now the time evolution of this object, of this wave function, is given by the Schrödinger equation. I put in explicitly h bar. We shall see the role of this h bar later. Okay, so we have again a potential term. And now if we take this equation and we couple it to the Poisson equation, again with the density given by this quadratic quantity, like all the physical observables on the Schrödinger equation. Yes? Ah, this would be a disaster. Thank you. It is not a heat equation, it's a... Okay. So this would be a system that I call Schrödinger-Poisson. Okay, so there's a lot to be said on this system, a lot on quantum mechanics. I just want to go straight to what can be the quantum Vlasov equation. Just a remark, so this equation doesn't fall from the sky. It actually comes an approximation of the n-body problem. Whenever we think about this kind of nonlinear Schrödinger equations, remember that if you take Coulomb interaction, which is behind this Poisson equation in 3D, then you make a weak coupling limit from the n particle, from the linear n particle Schrödinger equation, in a similar spirit that what we saw in the talks of Pierre-Emmanuel Chopin and others, except that the quantum case is somewhat easier because you do not have to control the gradient of the potential. So this would be the quantum world, this would be the classical world. So how can you make a link between these two systems, Schrödinger-Poisson and Vlasov-Poisson? So actually, in between, you have a magic trick, which is called the Wigner transform. So the Wigner transform is nothing else than an ingenious idea of actually Eugene Wigner, so it carries the name rightfully, to go from a wave function towards a distribution function. And that will be the key problem of the whole thing. What do we get? So the transformation is the following. You set up a quantity, call it W, that lives in phase space. Let's take everything in R3. And now what you do is you take your wave function, you bring in, I call it epsilon for the first, as the start, a scale, and you do a Fourier transform. Okay? So you do a Fourier transform with respect to this relative variable, this eta. So you take your wave function, you make center of mass and relative coordinates, and you bring in a scale at this point. That's very important for Wigner transform. It carries a scale. So the natural scale in the context of semiclassical limits is to put in h bar, our scaled Planck constant here. So then this new function, which you'll see the properties, depends on the scale that we have brought in here.
Where is V?
V is a velocity. This is just it's a dual variable of, this is a second space variable, so you make a doubling of coordinates. For insiders, that's of course the density matrix. So you set up the density matrix, you evaluate the density matrix at special center of mass and relative coordinates, and then you do a Fourier transform. Okay? You do a Fourier transform with respect to one of the position variable, and in some scaling you get some momentum impulsion. You go back to phase space. So if I say x velocity impulsion, you name it, is my phase space. So I construct out of physical space of the Schrödinger equation a new object that lives in what I call phase space by the force of this trick of doubling the variables and making a Fourier transform. Now what you immediately see is that this new function actually, it oscillates with negative values. So what you lose by this construction, you win a lot, but the first observation is it's a real valued function. So you start with the famous complex valued wave function, and you get a real function, but this function will oscillate. What you also immediately see that your density rho is again, and that's the key property of the Wigner function, one of the key properties is again, so let's just say we integrate out the momentum variable. So if you take this function and you integrate out the velocity or impulsion, however you call it, you go back to physical space and you get a non-negative, like you had in the case of Vlasov equation by taking the moments, so you exactly regain, and this holds for higher moments. So the current density will be the velocity times the Wigner function integrated, and the kinetic energy density will be just the square of the velocity, if you take the second moment. So that's the key idea of making this transition from classical to quantum. Before I present you what I call the Quantum Vlasov equation, I want to present one of the key tricks to get rid of this nasty property of this having negative oscillations. It's not a probability distribution. So what you do is you smooth it. Okay? This is also called a Hoshimi function. So in Japan in 1940, just at the onset of World War II, a Japanese physicist came up with this idea. And actually, one of the tricks when you do the limit from Schrödinger-Poisson to Vlasov-Poisson is use this Fushimi trick, as we call it, as a mathematical trick that helps a lot in doing the proofs, but it was already introduced by Fushimi a long time before. So the idea is you smooth it. So what does it mean to smooth? I denote by tilde that you take your Wigner function and then you make convolutions with a Gaussian in X and a Gaussian and you choose the variance of these Gaussians such that the product obeys the Heisenberg principle. So you could also say you coarse grain. You take your quantum object and you smooth, you coarse grain, you average over a phase space volume that obeys the Heisenberg principle. So if you do that, you end up with a function that is non-negative. Okay, so you take the minimum smoothing here. So that's in some sense you can say, let's say coarse-grained quantum mechanics is closer to classical mechanics since you have done this. And this is some remark, this is related to the coherent states. Okay? Now, the last remark before I go to the quantum Vlasov equation and its utility for the numerics. If you take this Wigner function and you do the weak limit, what you get is the so-called Wigner measure. Okay, so in some sense you can say you let go h bar to 0. Okay, so that's a mathematical object on its own. The Wigner measure as the limit of the Wigner function is non-unique. So if you pass from Schrödinger-Poisson to Vlasov-Poisson in 1D, you have unique classical solution of Schrödinger-Poisson, but for the Vlasov-Poisson system with measure-valued initial data, you have the notorious non-uniqueness. You cannot heal that by doing the trick that you come from the unique Wigner function to one unique Wigner measure. You have several, so you don't gain uniqueness of weak solutions of Vlasov-Poisson by just doing this trick, because there are several measures, it's not unique. And so finally, the Wigner equation that's my quantum Vlasov equation. Essentially consists that you get for this, when you do this transform and you take the Schrödinger equation, what you get is exactly the free transport operator. And then you get something what is a pseudo-differential operator. Okay, don't worry about it. You do Fourier transform, so it's no miracle that with the symbol of this potential and you couple that to the Poisson equation. So this would be the Wigner-Poisson system. And the limit of this pseudo-differential operator as h bar goes to 0, this is exactly what you expect from the Vlasov equation. You get exactly your term, and I call it V0 for the measure. So actually here you have some h dependent on all quantities. Okay, so you come back to Vlasov equation. So formally, it's relatively obvious that with this Wigner transform trick, you can expect to go from quantum mechanics to classical mechanics by doing this trick, and you can heal the problem that the Wigner function is not a non-negative probability distribution with this Fushimi trick. Now this is the basic idea. Now there is a classical problem that is to pass from Schrödinger-Poisson to Vlasov-Poisson. This was a very hard problem, and in 1993, this was solved by Lyons Paul and myself with Markovic. And this was the problem that you take the Vlasov-Poisson system as an approximation of the Schrödinger-Poisson system. Now, about 1 year ago, when I gave a talk on this issue in Nice, Oliver Hahn approached me and said, well, what we are doing actually is somewhat the inverse. Is there no way of getting this? Okay, so what is called the Schrödinger method in cosmology is the inverse procedure, approximate Vlasov-Poisson by Schrödinger-Poisson. So you say that your phase space function of the Vlasov equation is approximated by the Fushimi function plus some correction. So you say, instead of solving the 6-dimensional phase space of the Vlasov equation, I use numerics for the Schrödinger-Poisson system, which is in 3 + 1 dimensions, so it's expected to be much cheaper. And then I say, I approximate the function I look for, the Vlasov distribution function, by this Fushimi function, which is the good object to compare. You would not compare this negative oscillating Wigner function. So that's the equation you can use, and what you do for this is coarse-grained Schrödinger numerics. And that's what we already had done independently of this application in cosmology with Athanassoulis. He was at that time a postdoc of Thierry Paul at the École Polytechnique. And this is now the method where we have hope that this is more efficient than solving Vlasov-Poisson directly. And actually there is a nice talk by Michael Kopp, and Oliver Hahn is present here. So people starting to use this. And actually in 1993, this was introduced by Wiedrow and Kaiser. The precise reference is in the talk of Michael Kopp. So that's the idea of that's the quantum Vlasov equation. And you can use Schrödinger numerics in 3 + 1 dimension as an approximation for Vlasov numerics if you think that's more efficient. Okay? So we do this kind of numerics. The problem is we need highly adaptive codes that we don't have available in my group. So we work now on non-uniform FFT. Because in cosmology, you have these filaments and this concentration of mass, and the space is empty besides of dark matter that you look for. So you have to have very highly adaptive coarse-grained Schrödinger numerics. So this might be a very promising idea to solve a numerical method to solve the Vlasov equation by going back to the point of origin, not approximating quantum mechanics by classical mechanics, but classical mechanics by quantum mechanics. Okay, that's it.